Hi there, this is just the second lecture on, web lecture on the weekly tests that we've been doing in our third year class. And I just want to quickly go through some of the points to do with this test, just so that we can learn a little bit about what I was trying to get out with each of these questions. The first question over here was just I wanted you to pick up that in terms of this mechanism being incorrect, if the methoxide acts as a nucleophile and attacks this carbon over there, this methoxide can't leave straight away. What has to happen is that the pi bonds have to break first. So, in other words, we've got the OMe, we've got that, and when the methoxide adds there, the correct mechanism is that the pi bonds have to break first. And we go through this tetrahedral intermediate, and which looks like this, OMe, OMe, right? And then what happens is that collapses again and kicks out an OMe, and it can kick out either one of those, and so actually it doesn't really matter in this particular one. That's really, I just wanted you to point, to recognize that you don't just get something like that occurring. Some of you answered that no, what's supposed to happen is it's supposed to form an enolate, etc., etc. That's not the point. The answer to this is that this mechanism, as I've shown, is incorrect because this is showing an SN2 type of reaction, and that cannot happen on an sp2 hybridized carbon. Right, the next question, 2.1, was a little bit hard, and I actually accepted both answers that people gave, provided you gave me a sensible answer. So which side does the equilibrium lie? This is very difficult to answer unless you know how strong a base triethylamine is. And the point is, triethylamine is quite a weak base, and so from that point of view, the equilibrium actually lies to the left, because it's not strong enough to deprotonate there to form this, all right, to force the equilibrium over towards the right. However, if you did argue that this is a very acidic position and triethylamine is a weak base and this is very acidic, therefore you can push it over to the right, I would have given you the marks, but you would have had to have some sort of explanation. But the real explanation is that triethylamine is not strong enough to remove protons which are alpha to a dicarbonyl. I would not expect you to be able to do that, and I apologize for setting this question up, thinking through that, without having given you some sort of pKa table that you can work from to decide which is stronger or weaker. However, with LDA, this is different. LDA, you should know, because we use this a lot, and I have emphasized this in the lectures, that the lithium diisopropylamide, right, is a very, very strong base. And that will shift the equilibrium over to the right, very definitely, because it is a strong, strong base, much stronger than the pKa values of protons alpha to a carbonyl. And these are between 20 and 25. And the pKa of the acid of this is around about 40 or 36 or so. So it's much stronger. All right, so it moves over to there. And then, once again, this is a question that's come up quite a few times. This is just the formation of the silyl enol ether, which I'm trying to emphasize to you that you get this. Silicon and then 3 methyl groups, that would have been acceptable. TMS written there would have been acceptable. That's all fine. I think most of you did well in this, but just remember from a mechanistic point of view that triethylamine is not strong enough base to form an enolate. That mechanistically, like I've told you in class, you can think of the TMS like a hydrogen. It's like HCl. And so when you've got TMS and chlorine, it's like HCl. It can protonate the silicon, or silalate with the lone pair of electrons, kicking out the chlorine. Right, it's an equilibrium, and we then end up with an O with the silyl group on. That's silicon with 3 methyls, all right, which must be plus. It's just like this was an H on there, and we've got a Cl minus. And now what can happen is that the triethylamine, which is a weak base, is now strong enough to deprotonate and form the product over there, the silyl enol ether, and we're then left with the protonated triethylamine and the triethyl ammonium salt with the chlorine that's there. All right, that's just the mechanism that you should know. And this one, I actually made it pretty easy for you because I gave you the mechanism of it. So you just had to follow the connection of atoms. And a lot of you got this one correct. And so there wasn't any sort of problem with that, except where the double bond ended. So that's kicking in. Enolate is attacking, we're forming a bond between those two, but this double bond is breaking, going across, and so we end up with a double bond there. 1, 2, 3 carbons, 1, 2, 3. And the Br minus was kicked out. All right, this mechanism, out of interest, is actually, it's an SN2 prime mechanism, because it's not doing just an SN2 on this carbon, but it's going through like a conjugate addition. You don't have to worry too much about that, but you shouldn't be scared by this arrow push. You would have got exactly the same product had this carbon here done an SN2 reaction on this carbon there. Would have given you exactly the same product. All right, so hopefully that helped you a little bit with the second weekly test.